So starting off with some types, perhaps the most common type that we find is integer types in embedded systems, and C++98 had a problem in the sense that although we could support integers, the actual definition of an integer wasn't properly defined within the standard itself, so its implementation depended as to how many bits you get in an int. C99 addressed that with a standard set of integer types, and that was added into the C++11 standard as the header file c_stdint. So now it's possible to create integers with a finite number of bits, which will then be guaranteed. So, for example, 8 bits unsigned, 32 bits unsigned, and so on. Okay, so that problem has been solved in C++ since the 2011 standard came out. Enumerated types are another common sort of feature in lots of embedded systems, and the declaration and use overlaps what we have in C as well. So generally, when you've got an embedded type, we recommend using a type def, which then declares the enumerations, and these are then essentially just integer constants, which have a name which in the worst case could extend throughout the whole of your program if they've got global scope. And that's a potential problem because it's very easy to inadvertently have an enum where you've reused a name that's already in scope, and then that's going to cause you problems. Using enums is very straightforward. We can declare a variable of that enum type and then assign it a suitable enumerated value, and the compiler will check to make sure that the value we assign is part of that set. Implicit conversion can be convenient, but potentially it could also be a problem because there's lots of situations where bugs have arisen because implicit conversions between types have taken place and the author didn't realize what they were doing, and the compiler won't flag it up as an error. So implicit conversions to integers can be easy to write code, but it can hide potential problems. So we'll have a look at how we can solve that with modern C++. The compiler will check in C++ if you try making an assignment the other way. So if we go from an integer value and try to assign that to an enum, then the compiler will flag that up as an error in C++. We can overcome that with an explicit cast, and again that's fairly safe because it means that if we're using static cast, we can check to make sure that that static cast is legitimate by searching through the code and looking for all the static casts. But modern C++ has a better implementation of enumerated types, which is a enum class. So from C++ 11 onwards, rather than just having a type def enum, we can declare the enumerations as enum class. We don't need a type def statement if we're doing that because the enum class is automatically a type. And importantly as well, we can specify the underlying type. So no longer is our enumerated type just representing some arbitrary integer. We can specify exactly how many bits we want to have in that integer by using one of these integer types. When we want to access the enumerations, then they now have class scope. So if we've got an alternative enumeration which happens to use the same values as an earlier one, that's not a problem anymore because they have different scopes. So the enumerated values are part of the scope of the enum itself. Now that means that when you access an enum, there's an enum class, you always have to specify the scope. So it's a little bit more typing, but it's now safe. And additionally, the implicit conversion to an int that we had with the standard enum types is not allowed if we're using the enum class, so the compiler will flag that up as an error. We can still use a static cast if we have a good reason for wanting to convert the enum into a corresponding integer, but it no longer happens automatically. Okay, so that's a plus point in terms of safety. Now C++11 onwards also makes it possible to create variable declarations without needing to necessarily worry exactly what type of object you're declaring. Now for simple types like ints and characters, then specifying a type isn't a problem. But for more complex declarations, then sometimes it's not always clear to see exactly what type should be when you're creating an expression. So if we've got an expression that's used to initialize a variable, then the compiler knows what type that expression returns, so we can use the auto keyword to ensure that the type of A in this case is the correct type to match the expression. So that's good from an efficiency point of view. It makes the code easier to write and maintain. It also can catch potential bugs, because one of the most common bugs that you have in software is uninitialized variables which are used without having a proper value assigned to them. Well, if we're using the auto keyword, it's actually a compiler error if you've got an auto declaration here and you don't initialize it. Okay, so with auto, it guarantees that every variable you declare must have an appropriate initialization. We can also use the auto keyword for function return types, provided the compiler can work out what the actual return value type should be. So in the case of our setBit function here, then it's clear that the return type is actually going to be a uint32t. So the compiler can work that out. We don't need to worry about specifying it ourselves. Okay, so that makes it easier to write the code. Now, type defs are okay, but the syntax for type defs can sometimes be a little bit messy. So modern C++ provides an alternative that takes advantage of the using keyword that was originally added to the language for dealing with namespaces. So with using as a type alias, then what we have is the using keyword, and then what follows that is the name of the type that we actually want to define. And on the other side of the equals, we've got the actual type itself. So here UL is going to represent an unsigned long, so it's equivalent to if we'd written a type def unsigned long UL. So it's not a big advantage in that case, but it does make it a lot clearer when we've got complex type declarations. And in particular, things like pointers to functions are notoriously difficult to get right when we're writing the code. So with our type alias, if we want to declare a pointer to a function, so func is going to be a pointer to a function, and we can see that because we've got a star inside the parenthesis. So that represents our pointer to a function. It's a pointer to a function that takes a single uint32t argument and returns a uint32t result. Well, that matches the setBit function that we saw on the previous slide. So on the next line, we're using our type declaration here, func, to create a variable fpointer, which holds the address of our setBit function. If you like creating generic code, we can even use the alias as a template. Okay, so in this case, we've got a template parameter t, and we're saying that ptr is going to be a pointer to t, whatever t happens to be. T is just some type. And then to actually use it to create a variable, then on the next line we've got ptr angle brackets int, and then we're using that to declare iPointer. So iPointer is going to be a pointer to an int. If we wanted to point it to some other type, we can simply use that type as the template parameter. Okay, so it gives us lots of flexibility, makes the code easier and more efficient to write. Another common feature in C++ programs is to have constants. So C++ 98 onwards is very keen on the use of const as opposed to just having a plain variable, and the compiler is strict about checking to make sure that consts are read-only. So in this example here, we're creating a pointer to a constant uint32t, and the compiler will check to make sure that we only ever use that pointer to read the value, never to update it. Okay, so the compiler is very good at checking for that. So that's a good safety point. In modern C++, we can use the null pointer keyword to initialize that variable, that pointer. So null pointer is a better alternative for the traditional null macro, which was just representing a number 0, because null pointer is a pointer type. Therefore, the compiler can detect if you accidentally were to assign null pointer to somewhere where an integer is expected. You'd get an error, whereas you wouldn't necessarily get the same that with the null macro, which just expands to 0. So const is still important in modern C++, but one of the limitations of const is it's a read-only variable. It's not constant at compile time. So, for example, we can't use a standard const variable to set the size of an array. Modern C++ overcomes that by also including a const expression keyword. And a const expression is an expression that can be evaluated at compile time, provided all of its operands are known at compile time. So in this case, it looks like we're declaring a function called setBit, which takes a value n as its argument and returns the value of 1u shifted by that number of places. Well, that's a const expression, so if the value of n is known at compile time, then the compiler can work out the result. It doesn't need to actually code that up as a function. So here we're declaring a variable and initializing it by calling setBit. The compiler will work out the value that setBit 5 returns and use that as the initialization. So no function actually gets coded up and called in that case. So const expression allows us to declare constants which are constant at compile time. Literal values are frequently used in our programs, and C++ and C11 and C99 rather, sorry, allow us to have integer literals, for example, which are based. So normally an integer will be base 10, but we can also have integer literals in base 16 and base 8. C++ 14 extends that, so we can also have literal values as binary numbers, which is really useful if we want to set individual bits within the registers of our embedded system. Now, with a 32-bit register, then writing it all out as 32 zeros and ones might get a bit tricky to read. So we can also use the single quote character to delineate sets of bits to make it more readable. So the single quote is just ignored there by the compiler. So that's a useful addition into modern C++ for literal values that are integers and binary. Additionally, though, we can also create our own literal types. So we can create a literal type and give it a unit and scaling factors. So, for example, if we want to have an application where we're dealing with distances in meters and kilometers, we can declare this rather strange looking operator double quotes underscore km as a suffix that would allow us to create a value that's expressed in kilometers, and our function is going to translate that to the equivalent value in meters by multiplying by 1,000. Okay, and then we can use that anywhere where we've got a literal that's going to represent a value in kilometers. Okay, so in this case, 12.345678 kilometers will then actually be evaluated as 12345.678 meters. Okay, so we can create applications which have scaled literal values, and that can then hopefully make it easier to create code that behaves correctly, because the presence of those units allows us greater visibility about what's really happening in the program, and hopefully can catch any potential problems we might have as well. In a real-time system, we often have a requirement to deal with time values, and there is a built-in literal value that represents time in the chrono header. So if we're going to declare a time value that represents milliseconds, then here we're creating a variable tick interval. In fact, actually it's a constant because we're using constant expression, and that's going to be a value in milliseconds, and we're initializing it to a time of 1 millisecond. Okay, so that's good from a safety point of view because we can now represent times accurately. If we've got a real-time system with multiple threads, then it's quite likely we'll have situations where we've got shared variables which are accessed from different threads, and we need to ensure we don't get race conditions. So one approach to avoiding that would be to declare atomic access to that shared variable. And that's supported in C++ 11 onwards by using the atomic header. And if we declare an atomic type, such as here are MS-ticks, then when that code gets compiled, then the compiler will actually code it up typically with memory barrier instructions to make sure that we don't get situations arising where the value can be accessed simultaneously from two different threads. Now, you could argue that with a 32-bit int that perhaps isn't really necessary because that's not going to get interrupted in the middle of a 32-bit read or write, but certainly for longer or larger types, then the use of atomic can avoid those race conditions. Here's another example showing how we can take advantage of some of these new features. We've got SysTick handler interrupt service routine, which is commonly found in lots of embedded systems. It's very easy to create time-based code using the SysTick. And in this case, we're going to use our tick interval to update the tick count. And if we call the count function for our chrono milliseconds parameter, that will automatically convert it into the correct number of CPU ticks required to update our SysTick timer. Continuing with that, here we've got an example using both the chrono and atomic types with a delay. So we've created a simple delay function that's going to be passed in a delay time in milliseconds, and then we're going to access the atomic MS-ticks with this atomic load operator, and then we've simply got a spin lock that's going to be cycling around doing no op instructions until we get to the appropriate number of ticks given by our delay ticks count. Okay, and then here's an example where we could use the delay function to blink an LED with the specified time intervals. So 1 second and 500 milliseconds would be the delay timers there.
Doulos is a training company providing expertise and specialist training worldwide in all of the areas you can see on screen, from SoC design and verification, FPGA and hardware design, to embedded software and Python and deep learning. You can watch the rest of David's webinar, Modern C++ for Safe and Efficient Embedded Systems, whenever you want, by heading over to our website www.doulos.com/OD and registering for free. For more free tips and tutorials, visit the know-how area of our website, and don't forget to subscribe to our YouTube channel. Thanks for watching.